Pleasant day to everyone. Today we're going to discuss part 3 of module of the subject CE 4111, Highways and Railroad Engineering. So in this lecture, we are going to discuss an example of the applications for the vertical alignment of roads. In this example, we are going to design our curve using the speed reduction and economizing the alignment of curve. So an existing tunnel would need to be connected to a newly constructed bridge with a sag and crest vertical curves. The profile view of the tunnel and the bridge is shown. Develop a vertical alignment to connect the tunnel and the bridge by determining the highest possible common design speed for the sag and crest of equal tangent that is required. So we are given here the existing tunnel stationed at 0 plus 0, 0. Then we are given the station for the start of the bridge deck, which is at 0.366. So we call the start of our curve as PVC of the sag curve, and the end of our connection as PVE of the crest curve. So take note that for the elevation of the bridge deck, that is at 112 meters, and the elevation of the tunnel is at 100 meters. So what we want to do is to connect a sag curve to a crest curve with equal tangents. So in our equation, we're going to consider conditions and the given conditions, and we are going to use a design speed of 60 kilometers per hour. So what we will do is to determine the length of curves required to connect the bridge and the tunnel while keeping the connecting grid, this red line, as small as possible. So for our solution, we now have our sag curve. The beginning would be the PVC of the sag at 0, 0, 0 and elevation 100. So going up, we have here our vertical tangent of the sag. And then from the bridge, we have towards the bridge, we have your vertical curvature of the crest curve. And we have the vertical tangent of the curve at 0 plus 366 and elevation of 100. So the tangent point of sag will be connected to the tangent or to the curvature of crest curve. So this will be a common grid to them. So we have here our G1S, the first grid of the sag curve. Then we have the grid of grade 2 of the sag curve, which is the same or aligned to the connecting slope and is also the same as the first grade of our crest vertical curve. Then we have here your G2C, or the grade 2 or second grade of the crest vertical. So this point is the point of intersection for the vertical sag curve. Then we have the point of intersection for the vertical crest. For our solution, let L be your total length of curve, which is equal to 366 measured from the curvature of the sag to the tangent of the crest. Then we have LS, which is the length of the sag curve. LC is the length of your crest curve. And LG will be the length of your connecting grid. So from the figure, we can now say that L is equal to LS plus LG plus LC. So our first equation will be given by 366 equal to LS plus LC plus the connecting grid. So take note that for K, that is now equal to L over E, and that the value of E is simply equivalent to the absolute value of the difference between G1 and G2. So for the sag curve, L now can be computed as A times K, or LS, is equal to ES KS. And same for the crest curve, that will be LC times AC KC. And for our A values, that will be ES equal to the absolute value of G1S minus G2S. And AC will have the absolute value of G1C minus G2C. So from the figure, we can see that the connecting grid, this green line, is the same in grid as for G2S and G1C. Okay. This is your connecting grid or G-con. So also, we're given elevation 100 and elevation 112. So therefore, the height or the elevation, difference in elevation between your sag curve and the tangent of the crest curve is 12 meters. So we'll call now the distance or the elevation or height between the tangent and the curvature of the crest as YFC. And we'll have the height of the connecting grid is YG, and the height of the sag curve as YFS. Okay. So from here, we could also say that the summation of the heights of the crest, grid, and the sag is equal to 12 meters. For our values of y now is equal to a squared ls divided by 200 plus al g divided by 100 plus a squared times lc divided by 200. So ito, computation lang gamit ng grids. Okay? So with that, LG now can be computed as 366 minus LS minus LC. Substituting this in the y equation, we now arrive at this one. So we'll have only LS. So our equation now is in terms of LS and LC. Okay? So from the table of AASHTO 2011, we have here the design control for crest vertical curves based on the stopping sight distance, as well as design controls for our sag vertical curves. So since our design speed is at 60 kph, so we now look at the values of 60 kph for both crest and sag curve. So from here, we'll be able to get now the value of our K. So for the vertical, or the crest vertical curve, K now that we're going to use is 11. And for the sag vertical curve, that is equal to 18. Okay? From there, we now have our derived equation from y. And we are given that LS is equal to KS times A, and LC is equal to KC times A. So substituting now the value of K, S, A in our LS, and we're able to find the value of KC and KS. So substitute this in this equation, we'll arrive at a simplified simplified equation again in terms of the values of A. So for this, we can now simplify them by simply multiplying the third term by 2 so that we'll have all of our terms divided by 200. Okay, so simplifying this, we'll now arrive at 2,400 equal to 29 e squared minus 732. So this is a quadratic formula, quadratic form. Therefore, we could now solve this by quadratic formula, which is equal now to negative b plus b, or negative b plus or minus square root of b squared minus 4ac divided by 2a. So b is negative 732, a is 29, c is 2400, giving us a value of a equal to 21.368% and A2 equal to 3.873%. So again, do not use your shift solve as it may give us the wrong root or wrong value of A. So we're given two values of A. So which of this are we going to use? We're going to use 21.368. Masyadong steep yung ating slope and we do not want a very steep slope in our design. So our governing A now will be 3.873, which is our economizing alignment. And for our computation, AC now is equal to AS. So given now our diagram, the values from the table, TCPS, and our computed economizing A, which is 3.873%. So equal tangent curves, therefore ES is equal to EC. You now apply LS is equal to PS times A. That's 18 times 3.873, which is 69.713 meters. Then we have for LC, that is equal now to 42.603 meters. From there, we'll be able to solve now for the value of LG, okay, and as well as our stations and elevations. So for our PVC, it's at 0 plus 0, 0. So ang station natin for PVI will now be equivalent to L over 2. And then for PVP, PVI plus L over 2. And then PVC will be equivalent to PVT plus LG. PVIC is PVC plus L over 2 of the crest curve. And from PVIC, it should be equal to plus LC over 2 should be equal to 0 plus 366. Then for your elevation, you could just simply solve for the value of your heights y to solve for the elevation of PVT and PVC. Okay, so that's it for the applications of our vertical curves for the vertical alignment of road or highways. So thank you for listening. Again, for your references, we have the following books and